should take it slow.
Hello everyone, welcome back to another video. In this video we'll be exploring implicit and partial differentiation. So firstly, let's look at how we did differentiation in the video before. Just before, you would have seen a function that looks something like this. Y is equal to, say, x squared plus 5. Right? The y is always to the 1 power. But what if we had a function that said y squared to the x squared plus 5? What would happen when the y is raised to a power? Now, some people might just go ahead and write y is equal to the root of x squared plus 5, and then use the chain rule. But using implicit differentiation, we can make this much simpler. So let's say we have let's look at what happens if we were to differentiate y equals x squared plus 5. If we differentiated this, what happened is that we treat the y the same way we treat the x. We bring the power here is obviously 1, so we bring down the 1 to multiply the y, so we end up with 1y to the 0 power times dy dx. And of course, all of this is 1, so that's why we only get dy dx, and of course that will be equal to 2x. But now let's say we have the y squared equals x squared plus 5. Now what can happen is that we can say we can differentiate and bring down the 2 to multiply the y, and we can say 2y to the 1 power, because you reduce the power by 1, times dy dx is equivalent to 2x. Therefore dy dx would equal 2x over 2y. So that's how you work with it when the y has a power. Let's do another example. Let's differentiate x squared plus 3y plus 2xy squared. So we're differentiating y with respect to x. You have to remember to pay attention what you're differentiating with respect to what. We're differentiating y with respect to x, and so when we'll differentiate them piece by piece, so we'll have 2x plus 3 dy dx, because it's just y to the 1 here, dy dx plus 4 x y dy dx equivalent to 0, of course, because you differentiate the conjugate, you get 0. And then from here we will just factorize and solve for dy dx. Now let's do the same differential again, but this time we're differentiating x with respect to y. So since we're differentiating x with respect to y, we would get 2x dx dy plus 3 plus 4y dx dy, of course, equal to 0. And so by looking at it, you can see how it can change depending on what you're differentiating with respect to what. So this is simply how to do implicit differentiation, and of course you can apply the product rule, chain rule, and quotient rule as was shown in our previous video. Now let's move on to partial differentiation. Now partial differentiation refers to differentiating one variable while keeping the other one constant. Let's say we have a function f xy, so not just f of x but f xy, function in x and y, equivalent to x cubed plus 4x squared y cubed minus y to the fourth. Now again, we're going to find the partial derivative of x and the partial derivative of y. And the way we would write this, for the partial derivative of x, we would write it like this. So common delta f over common delta x. So what we will do here, we will find the differential of f with respect to x while keeping y as a constant. So we'll end up here with 3x squared plus 8x y cubed. Of course, because we're keeping the y as a constant, we just treat the y as another coefficient of the x. Minus 0, because if we're keeping the y as a constant, differential of a constant is actually 0, and therefore that's what we would end up with here when we just have the y by itself. And if we were to go the other way around and find the partial derivative of f with respect to y, this would become 0 plus 12 y squared x squared minus 4y cubed. Yes, that's partial differentiation and implicit differentiation in a nutshell. Thanks for watching. I'll see you next time.
Tell me pretty lies, look me in the face. Tell me that you love me, even if it's fake.